All right, hello everyone. Welcome to my channel. And this channel is for educational purposes. We take a look at some great theories of everything from the past, ancient and modern, and go deep into them, try to suss out some of the finer points and some of the points that you can use in your own life to help you. Today is our 504th video that we've done on Dewey B. Larson and his reciprocal system of theory. Mr. Larson was an American engineer, and he died back in 1990 at the age of 92, I believe. And he left behind many great books and articles as well. And some of his colleagues have written some things that are eye-opening as well. Larson was one of the few scientists to propose a universe made out of not matter, not energy, but motion. The universe of motion. And unlike some of his predecessors like Descartes and Hobbes, Arthur Eddington, Larson was able to parlay his universe of motion into a generalized theory of everything by defining motion as the relationship between space and time. And he also envisioned motion in a more generalized way as what he calls scalar motion. This is a motion that has a magnitude, but it has no specific direction. You can model some scalar motion if you take a balloon and you put dots on it with a magic marker or something, and then you blow up the balloon. All the dots will be moving away from each other. Every dot will be moving away from every other dot, but they won't be moving in any specific direction. Every dot will basically be moving in every direction, outward. And then if you contract the balloon, every dot will be moving inward, but in no specific direction. Each dot will be moving toward every other dot. And the outward motion Larson refers to as the progression, and this is really the source of the universe. This is the empty universe, and then manifestation occurs by kind of reversing that outward motion of the progression and turning it into the inward motion, which he refers to as gravitation. Larson took his two fundamental postulates that he proposed in 1959, and he, through a process of deduction, arrived at a theoretical universe. What his universe would look like if his two postulates were correct. And the first postulate is where Larson does most of the work. This is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then from arriving at his theoretical universe, by basically running his first postulate through his second postulate, which is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So Larson takes this kind of conventional understanding of math, geometry, and logic, and creates his theoretical universe out of his first postulate, and then compares his theoretical universe with the measured empirical universe of the legacy scientists that they have arrived at from laboratory experiments and compiled in their scientific tables. Some of Larson's books are results of that comparison, including this one here that we're looking at that is called Basic Properties of Matter. This book is primarily on chemistry. Larson arrives at equations for many of the basic properties of matter, such as the melting point or the compressibility or the specific heat. And then he applies them to all of the atoms and many compounds, and then compares them with the scientific tables. In many cases, Larson is able to more or less recreate the scientific tables strictly from theory. And in some cases, he's even able to improve upon the scientific tables from his theory, where the scientists are having trouble making measurements. Today we are looking at chapter 18 from this book, which is called The Retreat from Reality. Now, if you want a more thorough rundown of Larson's reciprocal system, the postulates and what they mean, flesh them out a little bit, you want to watch any of my first 474 videos on this subject. But for now, we're going to get right into the retreat from reality. Basically, I'm going to assume that you have some knowledge of the reciprocal system and can move forward. But I think actually this chapter is primarily theoretical, and Larson will probably be able to speak on his own here without me interjecting a lot of other information that you need. Okay, chapter 18, The Retreat from Reality. In the 8 chapters from 9 to 17, excluding chapter 12, we have described the general features of electricity, both current electricity and electric charges, as they emerge from a development of the consequences of the postulates of the theory of the universe of motion. This development arrives at a picture of the place of electricity in the physical universe that is totally different from the one that we get from conventional physical theory. However, the new view agrees with the electrical observations and measurements and is entirely consistent with empirical knowledge in related areas, whereas conventional theory is deficient in both respects. Thus, there is ample justification for concluding that the currently accepted theories dealing with electricity are, to a significant degree, wrong. This finding that an entire subdivision of accepted physical theory is not valid is difficult for most scientists to accept, particularly in view of the remarkable progress that has been made in the application of existing theory to practical problems. But neither a long period of acceptance nor a record of usefulness is sufficient to verify a theory. The history of science is full of theories that enjoyed general acceptance for long periods of time and contributed significantly to the advance of knowledge, yet eventually had to be discarded because of fatal defects. Present-day electrical theory is not unique in this respect. It is just another addition in the long list of temporary solutions to physical problems. The question then arises, how is it possible for errors of this magnitude to make their way into the accepted structure of physical theory? It is not difficult to find the answer. Actually, there are so many factors tending to facilitate acceptance of erroneous theories and to resist parting with them after they are once accepted, that it has been something of an achievement to keep the error content of physical theory as low as it is. The fundamental problem is that physical science deals with so many entities and phenomena whose basic nature is not understood. For example, present-day physics has no understanding of the nature of the electric charge. We are simply told that we must not ask, that the existence of charges has to be accepted as one of the given features of nature. This frees theory construction from the constraints that would normally apply in the absence of an adequate understanding. It is possible to construct and secure acceptance of theories in which charges are assigned functions that are clearly to be seen to be incompatible with the place of electric charge in the pattern of physical activity, once that place is specifically defined. None of the other basic entities of the physical universe, about 6 or 8 of them, the exact number depending on the way in which the structure of fundamental theory is erected, is much, if any, better known than the electric charge. The nature of time, for instance, is even more of a mystery. But these entities are the foundation stones of physics, and in order to construct a physical theory, it is necessary to make some assumptions about each of them. This means that present-day physical theory is based on some 30 or 40 assumptions about entities that are almost totally unknown. Obviously, the probability that all of these assumptions about the unknown are valid is near zero. Thus, it is practically certain, simply from a consideration of the nature of its foundations, that the accepted structure of theory contains some serious errors. In addition to the effects of the lack of understanding of the fundamental entities of the physical universe, there are some further reasons for the continued existence of errors in the conventional physical theory that have their origin in the attitudes of scientists toward their subject matter. There is a general tendency, for instance, to regard a theory as firmly established if, according to the prevailing scientific opinion, it is the best theory on the subject that is currently available. As expressed by Henry Margenau, the modern scientist does not speak of a theory as true or false, but as correct or incorrect relative to a given state of scientific knowledge. That is a quote. One of the results of this policy is that conclusions as to the validity of theories along the outer boundaries of scientific knowledge are customarily reached without any consideration of the cumulative effect of the weak links in the chain of deductions leading to the premises of these theories. For example, we frequently encounter statements similar to the following, quote, "The laws of modern physics virtually demand that black holes exist," end quote. And no one who accepts general relativity has found any way to escape the prediction that black holes must exist in our galaxy, end quote. These statements tacitly assume that the reader accepts the, quote, laws of modern physics and the assertions of general relativity as incontestable, and that all that is necessary to confirm a conclusion, even a preposterous conclusion such as the existence of black holes, is to verify the logical validity of the deductions from these presumably established premises. The truth is, however, that the black hole hypothesis stands at the end of a long line of successive conclusions, included in which are more than 24 pure assumptions. When this line of theoretical development is examined as a whole, rather than merely looking at the last step on a long road, it can be seen that arrival at the black hole conclusion is a clear indication that the line of thought has taken a wrong turn somewhere and has diverged from physical reality. It will therefore be appropriate in the present connection to undertake an examination of this line of theoretical development, which originated with some speculations as to the nature of electricity. The age of electricity began with a series of experimental discoveries. First, static electricity, positive and negative, then current electricity, and later the identification of the electron as the carrier of the electric current. Two major issues confronted the early theorists. One, are static and current electricity different entities or merely two different forms of the same thing? And two, is the electron only a charge or is it a charged particle? Unfortunately, the consensus reached on question one by the scientific community was wrong. The theory of electricity thus took a wrong direction almost from the start. There was spirited opposition to this erroneous conclusion in the early days of electrical research, but Rowland's experiment, in which he demonstrated that a moving charge has the magnetic properties of an electric current, silenced most of the critics of the one electricity hypothesis. The issue as to the existence of a carrier of electric charge, a bare electron, has not been settled in this manner. Rather, there has been a sort of compromise. It is now generally conceded that the charge is not a completely independent entity. As expressed by Richard Feynman, quote, there is still something there when the charge is removed, end quote. But the wrong decision on question one prevents recognition of the functions of the uncharged electron, leaving it as a vague something, not credited with any physical properties or any effect on the activities in which the electron participates. The results of this lack of recognition of the physical status of the uncharged electron, which we have now identified as a unit of electric quantity, were described in the preceding pages and do not need to be repeated. What we will now undertake to do is to trace the path of a more serious retreat from reality that affects a large segment of present-day physical theory and accounts for a major part of the difference between current theory and the conclusions derived from the postulates that define the universe of motion. This theoretical development that we propose to examine originated as a result of the discovery of radioactivity and the identification of the three kinds of emanations from the radioactive substances as positively charged alpha particles, or helium atoms, negatively charged electrons, and electromagnetic radiation. It was taken for granted that when certain particles are ejected from an atom during radioactivity, these particles must have existed in the atom prior to the radioactive disintegration. This conclusion does not seem so obvious today when the photon of radiation, which no one suggests as a constituent of the undisturbed atom, is recognized as a particle, and a whole assortment of strange particles is observed to be emitted from atoms during high-energy disintegrations. At any rate, it is clearly nothing more than an assumption. An extension of this assumption led to the conclusion that the atom is a composite structure in which the emitted particles are the constituent parts. Some early suggestions as to the arrangement of the parts gained little support, but a discovery in Rutherford's laboratory that the mass of the atom is concentrated in a very small volume in the center of the space that it presumably occupies led to the construction of the Rutherford atom model, the prototype of the atom of modern physics. In this model, the atom is viewed as a miniature analog of the solar system, in which negatively charged electrons are in orbit around a positively charged nucleus. The objective of this present discussion is to identify the path that the development of theory on the basis of this atom model has taken, and to demonstrate the fact that currently accepted theory along the outer boundaries of scientific knowledge, such as the theory that leads to the existence of black holes, rest on an almost incredible succession of pure assumptions, each of which has a finite probability, in some cases a very strong probability, of being wrong. As an aid in emphasizing the overabundance of these assumptions, we will number those that we identify as being definitely in the direct line of the theoretical development that leads eventually to the concepts of the black hole and the singularity. In the construction of his model, Rutherford accepted the then prevailing concepts of the properties of electricity, including the two assumptions previously mentioned, and retained the assumption that the atom is constructed of separable parts. The first of the assumptions that he added will therefore be given the number 4. These new assumptions are: the atom is constructed of positively and negatively charged components. The positive component, containing most of the mass, is located in a small nucleus. Negatively charged electrons are in orbit around the nucleus. The force of attraction between unlike charges applied to motion of the electrons results in a stable orbital equilibrium. This model met with immediate favor in scientific circles, but it was faced with two serious problems. The first was that the known behavior of unlike charges does not permit their existence at the very short distances in the atom. Even at substantially greater distances, they neutralize each other. Strangely enough, little attention was paid to this very important point. It was tacitly assumed, he's giving this the number 8, not sure. It was tacitly assumed that the observed behavior of charges does not apply in this case, and that the hypothetical charges inside the atom are stable. There is no evidence whatever to support this assumption, but neither is there evidence to contradict it, as the inside of the atom is unobservable. Here, as in many other areas of present-day physical theory, we are being asked to accept absence of disproof as the equivalent of proof. Another of the problems encountered by the new theory involved the stability of the assumed electronic orbits. Here, there was a direct conflict with empirical knowledge. From experiment, it is found that charged objects moving in circular orbits, and therefore accelerated, lose energy and spiral in toward the center of the circle. On this basis, the assumed electronic orbits would be unstable. This conflict was taken more seriously than the other, and remained a source of theoretical difficulty until Bohr solved the problem with another assumption, postulating entirely ad hoc that the constituents of the atom do not follow normal physical laws. He assumed, number 9, that the hypothetical electronic orbits are quantized, and can take only certain specific values, thus eliminating the spiraling effect. At this point, further impetus was given to the development of the atom model by the discovery of a positively charged particle of mass 1 on the atomic weight scale. This particle, called the proton, was promptly assumed to be the bare nucleus of the hydrogen atom. This led to the further assumption, number 11, that the nuclei of other atoms were made up of a varying number of protons. But here, again, there was a conflict with observation. According to the observed behavior of charged particles, the protons in the hypothetical nucleus would repel each other, and the nucleus would disintegrate. Again, an ad hoc assumption was devised to rescue the atom model. It was assumed, number 12, that an inward-directed nuclear force of unknown origin operates against the outward force of repulsion and holds the protons in contact. This assumed proton-electron composition quickly encountered difficulties, one of the most immediate being that in order to account for the various atoms and isotopes, it had to be assumed that some of the electrons are located in the nucleus, admittedly a rather improbable hypothesis. The theorists were therefore much relieved when a neutral particle, the neutron, was discovered. This enabled changing the assumed atomic composition to identify the nucleus as a combination of protons and neutrons, assumption 13. But the observed neutron is unstable, with an average life of only about 15 minutes. It therefore does not qualify as a possible constituent of a stable atom. So once more, an ad hoc assumption was called upon. It was assumed, number 14, that the ordinarily unstable neutron becomes stable when it enters the atomic structure, where, fortunately for the hypothesis, it is undetectable if it exists. As a result of the critical study to which the Bohr atom model was subjected in the next few decades, this model, in its original form, was found untenable. Various interpretations of the model have therefore been offered as remedies for the defects in this original version. Each of these adds some further assumptions to those included in the Bohr formulation, but none of these additions can be considered definitely in the main line of the theoretical development that we are following, and they will not be taken into account in the present connection. It should be noted, however, that all 14 of the assumptions that we have identified in the foregoing paragraphs enter into the theoretical framework of each modification of the atom model. Thus, all 14 included in the premises of the atom of modern physics, regardless of the particular interpretation that is accepted. I'm not sure. Thus, all 14 are included in the premises. Okay. It should also be noted that 4 of these 14 assumptions, number 8, 9, 12, and 14, have a status that is quite different from that of the others. These are ad hoc assumptions, untestable assumptions that are made purely for the purpose of evading conflicts with observation or firmly established theory. Assumption 12, which asserts the existence of a nuclear force, is a good example. There is no independent evidence that this assumed force actually exists. The only reason for assuming its existence is that the nuclear atom cannot survive without it. As one current physics textbook explains, quote, A very strong attractive force is needed to hold the nucleons in the nucleus, end quote. What the physicists are doing here is giving us an untenable excuse for the failure of the nuclear theory to pass the test of agreement with experience. Such evasive tactics are not new. In Aristotle's physical system, which was the orthodox view of the universe for nearly 2,000 years, it was assumed that the planets were attached to transparent spheres that rotated around the Earth. But according to the laws of motion as they were understood at the time, this motion could not be maintained except by continual application of a force. So Aristotle employed the same device that his modern successors are using, the ad hoc assumption. He postulated the existence of angels who pushed the planets along their respective orbits. The nuclear force of modern physics is the exact equivalent of Aristotle's angels in all but language. With the benefit of the additional knowledge that has been accumulated in the meantime, we of the present era have no difficulty in arriving at an adverse judgment on Aristotle's assumption. But we need to recognize that this is an illustration of a general proposition. The probability that an untestable assumption about a physical entity or phenomenon is a true representation of physical reality is always low. This is an unavoidable consequence of the great diversity of physical existence. When one of these untestable assumptions is used in the ad hoc manner, that is, to evade a discrepancy or conflict, the probability that the assumption is valid is much lower. All of these points are irrelevant to the question as to whether the present-day nuclear atom model is a representation of physical reality. We have identified 14 assumptions that are directly involved in the main line of theoretical development leading to this model. These assumptions are sequential, that is, each adds to the assumptions previously made. It follows that unless every one of them is valid, the atom model in its present form is untenable. The issue thus reduces to the question, what is the probability that all of these 14 assumptions are physically correct? Okay, I'm going to leave it there for today, and we will get into the second part of this chapter tomorrow when we resume. And thanks for tuning in today, and have a great day.